Here we're going to create a model of falling things. So we have an object falling, we're going to assume nothing is touching it, we're going to assume no air resistance. Also part of our assumption is the Earth is flat. We introduce this constant, g, which is a positive 9.8 meters per second squared. Remember that this constant is always positive. With these assumptions, our model of falling things is anything falling near the surface of the Earth is going to have an acceleration as a function of time that is constant as a function of time. It has a magnitude of g, and its direction is down. Down meaning perpendicular to the flat surface of the Earth. That may seem simple enough, but I want to highlight that how you represent this mathematically can depend on your coordinate system. Here I have a falling physics professor, and if I want to write a mathematical representation of the acceleration, which is a vector, I need a coordinate system. If I have positive x-axis up, say, then my acceleration as a function of time will have a magnitude of g, which is 9.8 meters per second squared. Since it's down, it will be in the negative x-axis. So I might rewrite that as negative g in my one-dimensional notation. If, for example, I choose a y-axis as my one-dimensional axis, and I have the positive y down, then my acceleration as a function of time will have a magnitude g, and it'll be pointing in the positive y-axis. What is always true in my model is that my vector for my acceleration points down toward the surface of the Earth, perpendicular to the flat surface of the Earth. The mathematics of it can depend on my coordinate system. I would write my acceleration this time as a positive g. Let's quickly look at a graphical representation of what this means. So I have a person here who's going to throw a ball up in the air, and I'm going to choose positive x to be up. And we know the acceleration as a function of time then will be negative g, g being 9.8 meters per second squared. And my model is going to be immediately after the ball leaves the hand, because the model for falling things means that nothing else can be touching it. So it only applies after it leaves the person's hand. And so it'll go up, and then it'll come back down, and I'm going to end my model, or my analysis, before the person touches it. It has to be immediately after it leaves the hand and immediately before it catches it where this model applies, because nothing else can be touching the object for this model to work. The initial velocity is going to be, with some value, is greater than 0. The initial velocity points in the positive x direction. And the initial position, well, let's say that's 0. Let's put our 0 at the position where the ball is. Our model says the acceleration is a negative g always. It's constant. That means during the entire throw, after it leaves the hand all the way up to the top and all the way back down, the acceleration is always a negative g, or negative 9.8 meters per second squared. What happens to the velocity? Well, the velocity starts with some positive value, and it has a constant negative slope throughout, given the acceleration. Note that it crosses 0 here in the middle. That's right at the top, where it comes to rest. And then after it turns back down, its position is negative, meaning it's pointing down. Before it turns around, it's going up, which means the velocity is up. This point right here is a turning point where the velocity goes through 0. And finally, the position starts at 0, it goes up to some maximum value, and then comes back to 0. At the beginning, the slope is large and positive, corresponding to this value of the velocity, and the slope decreases and this slope goes to 0, which is this value of the velocity. And then the slope turns negative and becomes increasingly negative as the velocity gets more negative as well. So that's our model of falling things. And remember, when we assume falling things, nothing else is touching it, including the air. Unless otherwise specified, we're going to always assume that falling things encounter no air resistance.